Welcome to Grand Rounds, doctors. Hope you've got your coffee handy because today we are stepping right out of those neatly highlighted chapters of your medical textbooks. We're not going to look at the human body as just some collection of independent parts. Instead, we're looking at the whole shebang, a single, exquisitely harmonious machine. Because as you get ready to treat real, complex illnesses, understanding this profound interconnectedness, well, that's what's going to elevate you from just a student of anatomy to a true healer. Let's get into this explainer.
So here's a question you literally have to ask yourself constantly on the ward. How does a single, localized action cascade through the entire patient? Just imagine a patient crashing with a severe systemic infection. You push a life-saving antibiotic into a single vein in their arm, right? But it doesn't just stay there. It immediately embarks on this incredibly complex journey, interacting with tissues and organs that honestly seem completely unrelated to where you just injected it. To really understand how we treat illness, we absolutely have to map out this remarkable physiological domino effect.
Arvind Gupta actually hits the nail on the head regarding this illusion of separation. Now, in med school, we study these systems in total isolation, mostly just to make the memorization somewhat bearable. But in reality, they are inextricably linked. Your organs are basically the ultimate multitaskers, constantly moonlighting across different systems. Take your patient's 206 bones, for example. Yes, obviously they provide structural support, but they're also incredibly busy manufacturing vital blood cells for the circulatory system. Or the ovaries, producing ova for reproduction, sure, but also secreting crucial hormones for the endocrine system. Absolutely nothing in the body works alone.
Okay, so we traditionally chop the body up into 11 major organ systems for the sake of learning. You've got the integumentary system acting as your protective barrier, the nervous system firing off electrical impulses, the digestive system breaking down fuel, you know the drill. But today, as we walk through an acute clinical case study, I really want you to view these not as a bulleted list, but as one living, breathing network. Because an intervention or a failure in just one of these lines of biological code literally rewrites the entire program.
And to really wrap your head around the sheer scale of that network, look no further than the cardiovascular superhighway. Inside your adult patient, there are roughly 60 to 100,000 miles of blood vessels. Think about that for a second. If you lay them end to end, they'd wrap around the Earth more than 3 times. It's wild. And this massive pipeline is exactly what delivers oxygen, white blood cells, hormones, and, crucially, your pharmaceutical interventions to every single corner of a sick patient's body.
All right, let's meet our patient. Now, for pharmacological modeling, science uses the mathematically standardized ICRP European male. But let's bring him to life. Let's call him Mr. Henderson in bed 4. He's a 73-kilogram guy presenting with a severe localized muscle infection, running a baseline cardiac output of 6.5 liters per minute. Now, he's about to receive an aggressive 100 millimolar bullets injection of a therapeutic drug. We'll just call it Substance A for now. Let's trace exactly what happens the second you push that plunger to fight off his illness. The very millisecond that therapeutic drug enters Mr. Henderson's vein, it gets completely swept up by the cardiovascular system. It's pushed forward by the heart, acting as this relentless pump, and gets oxygenated by the lungs over in the respiratory system. It enters this perfect closed loop of continuous delivery and return, navigating an unbelievably complex flow route through entirely distinct organs. It's basically a biological transit map.
And what's truly fascinating here is the body's strict division of labor. The arterial pool rapidly distributes our medication outward to all 79 organs to go fight that infection. Meanwhile, the venous pool, that serves as the cleanup crew. It's gathering the deoxygenated blood and the circulating drug right back up. And notice how the gastrointestinal and spleen outflow don't just dump their contents randomly. They are specifically funneled through the portal vein directly into the liver. It's the body's ultimate, highly specialized filtration plant.
Now, to really figure out if our drug is working, we've got to zoom way in. We need to shift from the macroscopic, gross anatomy of our 73-kilogram patient right down into the microscopic world, because this is where the real war against his illness is won or lost. Just consider the sheer volume of activity going on. Your patient's body is producing 25 million new cells every single second. It is entirely down at this cellular level that Substance A has to successfully deploy to save the patient. But here's the catch. Our drug doesn't just flow freely through an open pipe. It actually has to breach some incredibly strict biological borders. First, it travels down the vascular tube, then it diffuses across into the interstitial fluid, the fluid bathing all the cells. And finally, it has to forcefully penetrate the cell membrane itself. Whether it's targeting the brain, which is hogging 20% of our oxygen, or a specific infected muscle fiber, this 3-step microscopic crossing is an absolute, non-negotiable requirement for the medicine to actually work. So let's take a look at the battlefield, the muscular system. Inside the infected muscle's cellular space, our therapeutic bolus, substance A, gets right to work and undergoes a major chemical transformation. The cells metabolize it, converting it into a totally new byproduct, which we'll call metabolite B. But the process doesn't stop there. The muscle cells then kick this byproduct back out, across the interstitial fluid, and right back into the vascular space for whole body circulation.
Okay, so once that byproduct is back in the blood, the body's interconnected waste management team has to take over. The cardiovascular system plays transport, hauling the metabolite away from the muscles, but it relies completely on the digestive system's liver, the hepatic function, to actually clear the metabolite from the cellular space. And finally, the urinary system's kidneys step up to filter the resulting waste straight out of the blood, expelling it as urine. Literally, it takes 11 distinct systems, working flawlessly as one, just to clear a single drug.
When we pull Mr. Henderson's pharmacokinetic labs, this interconnectedness is just undeniable. You see a sharp, immediate spike in the vascular system right after you push the syringe. But then, just moments later, a secondary rise and eventual clearance happens entirely over in the liver. You're basically watching real-time proof of the muscular system altering a chemical and the hepatic system cleaning it up, seamlessly synchronized across time and space. It's honestly beautiful.
So, the ultimate takeaway from all of this? Diagnosing a muscular infection, or liver failure, or a neurological deficit in total isolation is a physiological impossibility. Our biological infrastructure is entirely codependent. I mean, the nervous system dictates the heart rate, the heart pumps the blood carries endocrine hormones, and those hormones regulate the kidneys. An illness in one system is inherently an illness in the entire network. That idea of biological separation, it's really just a convenient illusion we use to write textbooks.
As a future physician, you absolutely must carry this reality onto the ward. If a simple, localized injection requires the perfectly synchronized effort of 11 organ systems, 200 bones, 650 muscles, and tens of thousands of miles of blood vessels, just to metabolize, how does respecting this incredible interconnected web fundamentally change the way you heal your patients? Keep that in the back of your mind the next time you pick up a chart. Doctors, that concludes today's Grand Rounds Explainer. Let's get out there.